Welcome to Young Tuition. This is part of in-depth lectures on the climate change studies. There are many equations you can find in the related papers and books over the past decades. Fortunately, the fundamental equations, namely the basic laws in physics, are finite. So today I'm going to go through each of these basic equations one by one, so that you will have some ideas about what have been going on at theoretical levels in those climate change studies. The first equation is known as Stewart Equation. Stewart. Which was first published in 1858. And Stewart argues that the emitted energy of the hot object must be proportional to the absorbed energy. And he calls this absorption. Can we just rewrite this simple relation? Can be rewritten as emitted energy over absorbed energy equal to a factor of proportionality, S. And these factors depends on, among other things, the temperature of the object emitting the radiation and the surface reflectivity. Can we use R? Some textbooks use rho, the Greek letter rho. In addition, according to Stewart, other factors or variables might also be relevant. So can we just use Xi, indicating there are other factors that can be used to determine this proportionality constant. The second equation is called Kirchhoffs Law. This is published 2 years later. And the Kirchhoffs law can be written as Kirchhoff was considering the same phenomena, namely the thermal radiation. He argues that the emitted energy over the absorbed energy must be equal to a universal function. Can we use that as a K? Which the only variable is the temperature of the object emitting radiation. From these two equations, you can see that Kirchhoff's law is similar to Stewart equation. But Kirchhoff didn't acknowledge the publication 2 years before him. Nowadays, Kirchhoff's law has been extended as a simple relation that said the emissivity epsilon at a particular frequency must be equal to the absorptivity at a particular frequency. Can we use alpha to represent this absorptivity? Or sometimes it's called absorption coefficient. We'll go to some detail in the future. So this is the two forms of Kirchhoff's law, and which has been widely used in studying climate. The third equation is known as Planck equation or Planck function. And in some textbooks, it is also called as Planck Blackbody radiation law. So the form of this, we use letter B to represent Planck function, which is a function of the frequency and the temperature. So that is equal to mathematical expression is 2h, a constant, c squared, c is light speed, divided by, sorry, it should be if you have two different forms, equivalent form. If you use the frequency, that's be the mu to the power of 3 divided by c squared. C is the speed of light. And they multiply factor, which is E, h is a Planck constant. And frequency, we use mu for frequency, divided by the K multiply the absolute temperature, take 1, where K is a Boltzmann constant and h is a Planck constant. So the mu is a frequency. So in Planck function, by the way, Planck is a student of the Kirchhoffs. So therefore, he continued Kirchhoff's research, and by introducing what we nowadays called the quanta or quantum, and by treating the radiation as photons. And so this is also, therefore, Planck function is also widely used in physics because it was considered as the beginning of the modern quantum mechanics. Alternatively, Planck function can also be written as function of wavelengths, because we know there's a simple relation between the frequency and wavelengths. So we have C equal to lambda multiply frequency. So if you do this simple, just replace this variable, the Planck function can also be written as, this time we use a 2h, this is a c squared over there, our denominator, numerator, divided by the lambda, the wavelength, to the power of 5. And this factor will be the same, except depending on which variable you use. That can be, if you use lambda, in this, that will become hc divided by lambda k t, and take 1. So Planck function has two different forms depending on what the variable you use. And in many cases, and the Planck function is also written as a function of what we call the wave numbers. So another variable we can use called wave number, So wave number is just one, you can simply consider it's just 1 over lambda reciprocal. Or sometimes you could 2 pi, you could 2 pi here, 2 pi over here. So wave number is very similar to the frequency. Okay, we'll talk about this detail in the future. Before we go further, perhaps we need to draw some of the graph of the Planck functions. And if you use, or perhaps we don't have much time this time. Just go back here. Yes, let's just continue to talk about the basic questions. We're just discuss the graphs of the Planck function in the future. Now, one thing I must add here is that when Planck introduces a function, he actually modified Kirchhoff's law slightly. In his theory, he assumed that the emitted energy, E, over the absorptivity at a particular wavelength or particular frequency is equal to this his function called B. So notice that the form of these related equations are slightly different. And we're going to discuss these implications in the future. Let's just move on to the fourth equation. The fourth equation is due to the Einstein, Albert Einstein. Or before we go further, we must have also mentioned another basic equation. Can we say study this first? Its name is called Stefan-Boltzmann law. Stefan-Boltzmann law was experimentally determined at the beginning, but later, after Planck put forward his new theory, then the Stefan-Boltzmann law can be derived by using Planck function. So Stefan-Boltzmann law says the intensity of Blackbody radiation can be simply written as a constant sigma multiply the T to the power of 4. Okay. This is for the Blackbody only. So we're talking about the Blackbody in depth in the future. But here we just mentioned that both Stefan-Boltzmann law can only be applied, strictly speaking, to the ideal object called Blackbody. So actually, these formula can also be obtained if we from the Planck equation. By the way, the Planck equation can be rewritten as, so basically the Planck function actually represent the density functions. So that is what is called the energy density. So can we sometimes we use the U lambda or UV. So that is a alternative notation for the Planck function. So this is called energy density in space. Alternatively, you can consider this is a number of photons per unit volume. There is a simple relation between the energy density and the intensity of radiation. Intensity is the power divided by the area. So there is a simple relation. Can we use a mu here to represent the intensity at a particular frequency is equal to the Planck function, or we can use U and V, multiply the speed of light and divide by 4. So that would be the spectral intensity. By integration of both sides, so in this way, if we integrate that, if in order to obtain the intensity of any frequencies, then we can obtain this simple, we can theoretically derive the Stefan-Boltzmann law. So that is to say, if just integrate that from 0 to infinity, and we will get the Stefan-Boltzmann law for Blackbody radiation. Okay. So these are just some of the related equations associated with Stefan-Boltzmann law, which bridge the early Stefan-Boltzmann experimental observation and the theoretical result by Max Planck. The next equation is due to Albert Einstein. It's called Einstein absorption and emission coefficient. After Max Planck put forth his theory on blackbody radiation, and nobody paid much attention except Einstein. So one of the later related work by Einstein about 20 years later is reconsider this issue from perspective of energy transition between two energy levels. Because in 1900, Planck just simply assumed that the radiation can be described by particles known as photon, but he didn't have any idea what's going on at atomical and electron levels. So it is Einstein who actually added some gradients to this description for the blackbody radiation. To cut the story short, perhaps I just want to mention that Einstein derived a similar equation for the Planck function. So nu and temperature T can be simply written as, in this case, that is by the three coefficients. So one is called spontaneous transition, spontaneous absorption. So that is another is B2, another is a B21, and this is fact over here. That is still the same. So this is called H mu, which is a photon energy, divided by kT. T is a Boltzmann constant. T is absolute temperature. So these three coefficients can be explained, can be compared with Planck equation, Planck functions, so that you can see that Einstein provide the first interpretation, description of the blackbody radiation at molecular level. Next, we're going to talk about another basic equation. Write down the name first. Schwarzchild equation. It is called Schwarzchild equation. It is also known as radiative transfer equation. So that is the same equation. It's called radiative transfer equation. If you want to know how the solar radiation interact with atmosphere and how the infrared radiation by the surface interact with atmosphere, and you have to use a Schwarzchild equation. And this equation idea is rather simple. They just assume that they can find the gradients of the radiation can we use the intensity along certain direction, and this gradient must be equal to the absorption, take a plus emission. Consider a medium which can not only absorb the radiation, but also can emit radiation. So in this case, the change in the incoming radiation, the gradients of incoming radiation intensity must be determined by both the absorption and emission. Of course, in many textbooks, this equation is simply written as di mu. Now, when we use mu here, we mean that we are considering a particular frequency. That mu here, ds or dz. I prefer use z because ultimately we have just considered the vertical radiation transfer. And that can be simply written as absorption. And also by assuming absorption is proportional to the incoming radiation intensity. So we can use alpha nu here, and then multiply the incoming intensity. That implies that we assume that the absorption n is proportional to the incoming radiation. The second term can be simply written as, can we use, in many textbooks, we use J mu here. So this is a basic form of the Schwarzchild equation. Schwarzchild is famous for his contribution to Einstein's general relativity, because he was the first person to find an analytical solution to Einstein's general relativity in a special case though. So therefore, this name is well known. But unfortunately, if you just go to some depths of the research papers who use this radiative transfer equation, you will find that there are some conceptual consistencies. We'll talk about these issues in the future, but just bear in mind the Schwarzchild equation can also be used to describe the so-called the photon scattering phenomena process. So if you go to recent papers, you will see that the Schwarzchild equation can be further written as by considering other terms. For example, the di mu, and over this time, they can also rewritten this as what we call the optical depths. Can we use tau here? Use tau here. And in this way, this part will become simply as the mu, the incoming intensity. And of course, and in this case, these we have to multiply this a little bit, because we have in this, to do so, we have assumed we have the optical depth is defined as, so dz is defined as alpha mu multiply dz. Sorry, other way around. So d tau, not dz. D tau is equal to alpha mu multiply dz. So this tau is called optical depth. Okay, we're talking about this different form of the radiative transfer equation in the future. Next would be ideal gas law. Okay, you must have learned ideal gas law in high school. Ideal gas law. The ideal gas law is useful to describe the atmosphere locally, because ideal gas law is derived for the isolated system, in which the temperature is uniform, so is pressure. But in the atmosphere, we know that the temperatures varies from surface of Earth up to the top of atmosphere. Therefore, we cannot use ideal gas law apply as a whole to the atmosphere. But you will find that it will be useful if to study some local thermal equilibrium phenomena. Actually, someone has applied this ideal gas law to determine the surface temperature based on the air density and the pressure. And actually the result is remarkable. So bear in mind that we have in some cases can apply some very basic simple law in physics to study the seemingly complicated atmosphere. Apart from ideal gas law, of course, another thing we have to mention is that this is Newton's gravitational law. Because after all, we are studying the Earth. We are studying the phenomenon near the surface of Earth. Can we just draw the Earth? So that is Earth. So what we are studying in what we so-called the climate is basically the, can we just redraw this picture? So let me see. So this we are studying atmosphere. Can you see? We are studying atmosphere around the Earth. Can we use a different color to represent the Earth itself? A mud, okay, a mud. This is Earth at the center. Actually, the thickness is atmosphere is very. The atmosphere is very thin compared with the radius of Earth. Although we have many detail we have learned about atmosphere, but bear in mind, as a whole, the atmosphere is very thin compared with the radius of Earth. And according to Newton, the gravitation due to the Earth and were determined by mg at any position. So at any position near the surface or above the atmosphere, and that force, the gravitational force, can be written as F equal to mg. So what is g? If you remember the high school physics, that g will be determined by the gravitational constant, capital G, multiply the mass of the Earth and divided by R plus h squared. So h, this is h, that is the height from the ground, and R is the radius of Earth. So that is why you will see that if you talk about the temperature and also as well as pressure, you will see that you will see the vertical distribution of both the density, the temperature, and as well as the pressure of the air, of the atmosphere. Okay, so that is Newton's gravitational law is also one of the basic equation. Can we move on to, let's just go to another equation. Let's just check the number, number 9. That is another type of equation. It's called Navier-Stokes equation. Because we are studying primarily about the fluid, because the atmosphere are made of gas. So gas can be treated as one of fluid, which has a distribution of the pressure, the velocities, and the densities. Of course, temperature. So basically, we need to describe each of these particles or air molecules what can we do? Can we just do some symbolic description? So this atmosphere, if this is atmosphere, we just draw some vertical cross section, the columns. Just use different color. So this is atmosphere, and this is ground. This is ground. So therefore, you can imagine that if there are many particles in the atmosphere, because of gravity, and the density will change towards the higher the altitude, sorry, the less molecule will be. In fact, 90% of the air molecule is under perhaps 10 to 20 kilometers. That is air molecule. But air molecules are not static. They are constantly moving. So you can imagine that the velocity of each molecule will be different. So this molecule might go that direction. This molecule might go that direction. It's a random motion. And also collision also constantly happen. So this is that is a challenge for people to describe so many particles at the same time. Still, thanks to the Isaac Newton, we know that each particle must obey the Newton's law. Okay. So each particle, for one particle, Newton's second law says that mass multiplied acceleration were equal to the force acting on it. Okay, but if you just build an equation for each particle, then the number of the equation is just astronomical. It's too difficult to solve, almost impossible to solve. Then people work out some of particular algorithm to solve this type of equation called they can divide this atmosphere into finite elements. So if I just draw one of them, so they just, instead of start a single particle one by one by using Newton's law, they just say, well, why don't we just consider cells? Can you see? Can you see cell? This cell could be anywhere you can see. Can you see that? And each cell may contain a number of particles. Okay, so that is how that Navier and also Stokes first introduced this equation to describe these elements. Can we just do one more? Can we draw something more? Can you see that the number of or density of the air are different? Okay, and of course we cannot illustrate the velocity. Velocity is also different, and as a whole, from point of view of thermodynamics, the temperature is also different or time dependent. So you can imagine that this equation is very challenging in terms of in order to find the equation for each particle. But but if you use a finite number of elements, it's called the finite element method. Then we can actually build equation for each cell. And by considering each cell has continuous fluid, and we still cannot, we don't have to deal with individual molecules. So this is idea behind the Navier-Stokes equation. So what do they argue that? Instead of talking about this single particle or single molecule, we can just focus on, and just illustrate that, can we just focus on particular cell? Particular cell. So this equation is for particular cell, okay, particular cell. And in general, the force must be involves many internal friction. So instead of dealing with a particle, they are dealing with fluid, like jelly. So that is this if you cut this into a cube, then you will see that the force can arising from its neighbors. Okay. Can we use a sigma over here to indicate there must be over one force, okay, interaction between two adjacent or between the particular element, between the particular cell and or agent and his neighbors. So this question in general, we can rewrite this equation as, can we divide this as a vector in general? So acceleration can be simply written as the sigma of Fi divided by the mass. Okay, so the mass of this particular cell. Okay, that is idea of Navier-Stokes equation. And Navier-Stokes equation is such that we can deal with large number system. In this case, the atmosphere, by just you introduce a finite number of elements, so that equation based on Newton's second law, we can build this. We can discuss the motion. So if you can describe the motion of each of the cell, then we should be able to obtain the density distribution, velocity distribution. Okay. Nowadays, it's handy by using computers. You can use colors to indicate the different values. So you will see after you work out the solution for a period of time, say 2 minutes, you can replay that solution so that you can generate the fluid dynamic that visible. You can visualize fluid dynamics. That's what have people in weather forecast has been used, this basic equation. Of course, the actual equation, the general form of this equation, it can be a little bit abstract. So basically, the general equation can be written as a density multiply and the partial derivative of velocity of a particular cell, or sometimes called a pulsar. And that is is partial derivative, delta t, plus we have used the notation in the vector and field analysis. So we have used the der. The delta is just like the derivative gradients and multiply the velocity, which is vector. So that this part would be acceleration. So this part would be acceleration. And the second, on the right-hand side, we regard the density of gravitational acceleration. So that is a contribution from the gravity per unit volume. See, normally we write gravity as W equal to mg. Okay. If you divided this volume on both sides, we will get the density multiply the gravitational acceleration. And also, in addition, we also have the pressurized, due to pressure difference, the gradients in pressure can also generate the force, such as buoyancy, Archimedes buoyancy. That would be part of this term. And in addition, of course, there are other terms which can just write down here as nu. It just as an internal coefficient. So this delta is called Laplacian. It's called a Laplacian operator. So this der, which equal to the partial derivative xi plus der xj, and it's partial delta. So the delta y, delta z, k. Okay, and this is Laplacian operator. So this dot is just, so this is a square, is sometimes as an upside down delta. That because we were saying second derivative, partial derivative. That is just a notation in the calculus, y and the square. Of course, the Navier-Stokes equation can become more complicated if you introduce a particular coordinate and a particular definition of the element. Okay. Anyway, so that is in principle, and we can that is part of, so this equation is provided the basis for what we call the CFD, a computational fluid dynamics. Of course, this CFD is useful to visualize the clouds and airflow, and so that people will have some, the impression that you are dealing with the fluid. But those patterns generated by computer may or may not be actual the case. So care must be taken when you see that nowadays people always publish some computer generated fluid dynamics to impress their readers. If you only want to study the climate, I can tell you what, the CFD is not much help, because if you want to study the climate instead of weather, perhaps I will talk about this issue next time, then if you just want to study climate change, the time span, the period, you are not interested to the local and the change in the short period of time of the pressure, the temperature. When you study climate change, we often refer to relatively long period of global means, such as what would happen over the 1 century, or perhaps 1 billionth time, 1 billionth years. So that is objective for climate studies. But nowadays, that if you just dig out any research paper or books, the author attempted to mix them up. On the one hand, they're talking about they are dealing with climate change issues. On the other hand, actually they are focused on the local weather phenomena, such as bushfire or the weather, the temperature, local temperature. Anything else? Oh, before we go, we have mentioned other. This is a basic equation I also have to tell you. That is a 3 equation. We have used one of them. Can you guess what we're going to talk? That's what is called heat transfer, or called a heat transfer. Equations. Of course, we know heat transfer actually refer to the thermal transfer. Okay, thermal energy, which is transfer, not heat. Heat is old and is not a correct concept in physics. So when I talk about heat transfer, let's just follow the tradition. You should understand this is actually talking about the thermal. Okay. Thermal transfer equation. So then then by using thermal transfer, then you can compare with the radiative transfer equation. Okay. But to be specific, we have 3 ways for the thermal energy being transformed from one object to another. So one is called conduction, thermal conduction. Another is called convection. The third one is radiation. Okay. If we just use I for the intensity of radiation, or also the intensity of heat transfer, then the conduction can be simply written as a constant K. this is not Boltzmann constant. Can we put the C here? This is for the conduction. Multiply the temperature gradients. So we can, if just for one dimensional, we just use the dt and the dz. Okay, that's just one dimensional. This is a temperature gradients. So in general, we can say that I is equal to and kc and delta t. So delta t. So this is a general form. This is called the temperature gradients. It's called the temperature gradients. Okay. So the origin of the thermal transfer is originated by the presence of temperature gradients. If the two objects have different temperature, the heat will spontaneously transfer from hot one to the cold one. Okay. So that is a special case. A second one is convection. Convection, for example, so when airflow passing the hot material, object like your computer, they can carry out a certain amount of the thermal energy away because originally the temperature is much colder than the temperature of the hot object. So again, we would expect that the intensity of the convection will be proportional to the constant. Can we just write this constant as h, not Planck constant? It's convection. Can we just call it beta? Okay. And then there's also the temperature difference. Can we use delta? So that's delta. So that would be, can we use delta? That is surface temperature. There's a temperature in the distance. Take the temperature of surface. And the third thermal transfer equation, we have learned that is simply equal to the difference between the two black body. And that can, if that's between two black body, so we can simply write this as T1. Can we call this the surface? Can use T1, T2, that'd be fine. Okay. So depending on which object is hotter, A and B, so that radiation in this case is for between two black body. Okay. So that are the three equations called heat transfer equations. Oh, perhaps we can also mention the last one, just in addition to the Navier-Stokes equation. So when we started the, can we just write the name down first? You know him, called Bernini. Well, I prefer Bernini. Bernini. Some people call it Bernini. I just call it Bernini. Okay, Bernini. And Bernini equation simply says if the fluid has a common velocity, such as, for example, if the fluid goes through this tube with different diameter, internal diameter, and you will see that the if you just follow each of these, it's called the fluid line here. That represents the direction of how the velocity go. Okay, this is horizontal. Of course, you can put it as a vertical, because hot air will go up, and cold air move down because of gravity, and also as well as the thermodynamics. So in this case, Bernini has the simple equation. In this case, he argues that the force Bernini equation can be simply written as the P, the pressure, plus half rho is the density of the fluid, velocity square, plus and GH, rho GH. G is gravitational constant, gravitational acceleration, or equal to a constant. So Bernini's equation is simply the different form of energy conservation or work energy law applied to the fluid whose float rate can be described by a single velocity. Okay, so we still can use Bernini equation to study some of the localized phenomena. For example, if you are 100% sure that air is go up, then you don't have to invoke the Navier-Stokes equations. Well, I hope this introduction will provide you complete pictures about what basic physical law have been applied to study climate, namely the surface atmosphere system. Okay, enjoy your watching, and have a nice day. Goodbye.